Okay, welcome to Mixed Strategies. This is always one of I kind of think of this as one of the cornerstone lessons we have. It's not one of the easier ones within game theory, but incredibly important, incredibly useful in terms of thinking about real world issues. I'm not I don't think that when you're out in the real world you're going to plot these out. But the idea of thinking behind what you should be doing in these particular scenarios is crucial. Studies that have looked at what do professional athletes do in various situations show that they implicitly figure this stuff out. So this is wonderful lesson that we're going through, and the idea behind this we'll explain in just a moment. So what do we mean by a mixed strategy, or why do we use it, which we'll start with. The reason we use it is there are many games that don't have an easily identifiable Nash equilibrium. So there's some games where you put up the 2x2 matrix or whatever larger matrix of possible outcomes, and you'll realize there's no Nash equilibrium to the game, at least not one in pure strategies. Even though if it doesn't have one in pure strategies, it will have a mixed strategy Nash equilibrium. Every game that has a finite number of strategies has at least one Nash equilibrium. But it could be a mixed strategy Nash equilibrium. So it could be a Nash equilibrium where there's no one outcome that's played 100% of the time by both players, but instead the players should be playing a strategy some probability of the time. They'd play one particular strategy and play a different strategy some other probability of the time. So every game has at least one Nash equilibrium, but it could be a mixed strategy Nash equilibrium. So what do we mean by a mixed strategy? Well, it occurs when a player randomizes the actions he or she will take. So no longer are you choosing, oh, I'm going to confess if you're in a prisoner's dilemma, or I'm going to defect, and that's just what I'm going to do 100% of the time. A mixed strategy occurs when you have assigned some probability you will choose to confess or defect if it's a prisoner's dilemma game. Now that's a bit of a silly example, as we know there is a dominant strategy you're supposed to confess in that one, but there are plenty of games where there is no dominant strategy. Sporting events are kind of classic for this. Suppose you're in a tennis match, right? And you could try to hit to tennis is probably bad for me because I'm sure I won't get the terms right. You could go for try to aim your serve more towards the middle line or the outside. Is that the baseline? No, baseline's farther back. But anyways, you could aim it for the left side or the right side of the area you can hit into. You don't want to do the same side all the time, right? If you 100% of the time are hitting to the same area, you're going to be pretty easy to beat. You need to randomize your actions. Likewise, your opponent needs to choose which side to prepare for, or which side to plan for a little bit more often, some percentage of the time. And if the opponent always planned for the same side, they'd be easily exploitable. In sporting events, in competitions, mixed strategies are crucial. If you do the same thing every time, you will be easily defeated. Basically, you will be exploited by not playing optimally. So every game has at least one mixed strategy Nash equilibrium, although sometimes we call this null, which just means it's a pure strategy. So every game has a Nash equilibrium. It's the key point. Even games where it will look like they don't have one, but a game can have both pure and mixed strategy Nash equilibrium as well. To go through this, we are going to go through one example through the video. We'll also be doing far more in class. So pitcher versus hitter is the example, right? This is a pretty classic case where I'm thinking you'll think through this without even putting up the payoff matrix, and you'll realize, yeah, there's not going to be a pure strategy Nash equilibrium. So pitcher could throw a fastball or a curveball, right? The hitter or the batter could prepare for a fastball or a curveball. Now, without putting up the payoff matrix, you should be thinking there's no way there could be a pure strategy Nash equilibrium here, because the pitcher will want to throw whatever pitch the hitter is not planning for, right? So if the hitter is planning for a fastball, the pitcher will want to throw a curveball. But if the pitcher's throwing a curveball, the hitter would want to plan for the curveball. But if the hitter's planning for the curveball, the pitcher would want to throw the fastball, and so on. And there's no outcome where they're both happy, right? At any given outcome, one of them would want to switch his or her choice. Now, I contrived a payoff matrix that deals with the probability the hitter will get on base with any one pitch. This is completely made up. But you see what happens if the hitter plans for the fastball and a fastball is thrown, the hitter gets on 7% of the time. The other outcome, the percentage the hitter doesn't get on base, that's, you can think of that as the pitcher's payout, right? 93% of the time the hitter doesn't get on base, the pitcher's happy about that. So the payoff 7%, 7 and 93. If the hitter plans for the fastball but the pitcher throws a curveball, well then the hitter only gets on base 2% of the time on that pitch. 98% of the time, the hitter doesn't get on base, so you could think of this as 7%, the higher number being good for each party, right? The 98 is better than the 93 for the pitcher, so that's an extra percent of the time the hitter doesn't get on base. If they both plan for the pitcher throws the curveball and the hitter plans for it, well, the hitter gets on 8% of the time now. If the hitter is planning for the curveball but a fastball is thrown, it's only 1% of the time. And as you can note, this is a zero-sum game. The higher numbers represent better outcomes for each party. Now, intuitively, I thought you'd probably pick this up right away, but even not intuitively, I'm guessing, you look at the numbers, it's clear there's no pure strategy Nash equilibrium. If we're down in the lower left-hand quadrant, well, the hitter's planning for the curveball and the pitcher throws a fastball, so the hitter would want to switch to prepare for a fastball, right? Would want to go from 1% to 7%. But if the hitter's planning for a fastball and the pitcher was throwing a fastball, the pitcher would want to switch to throw a curveball because 98 is greater than 93. But if the hitter is planning for a fastball and the pitcher throws a curveball, the hitter would want to switch to plan for the curveball to go from 2 to 8%. But then if the pitcher's throwing the curveball and the hitter's planning for the curveball, the pitcher would want to instead switch to a fastball, and we're right back where we started, and we see there's this little loop. Nobody is ever content at any one, or not nobody, there's always at least one of them that wants to switch at any of these four outcomes. So there's no pure strategy Nash equilibrium. Hitter wants to plan for a fastball if a fastball is pitched, plan for a curveball if a curveball is pitched. The pitcher wants the opposite. Right? The pitcher always wants to throw whatever pitch the hitter is not planning for. So what should each party do? This is where I think it takes some time for this to sink in, on like exactly how it works. But what each party has to do, as long as they have an opponent who's playing optimally, is they have to not do the same thing every time. Right? They can't, if the pitcher can't throw a fastball every time, or he or she will be easily exploited. So the pitcher is going to have to throw some fastballs and some curveballs. They're going to have to mix up the probability that they're doing this. Because if the hitter finds out what pitch the pitcher's throwing every time, the hitter's going to do far better and the pitcher's going to do far worse. So each party, in essence, is trying to prevent the opponent from making an easy decision. Now, one thing to note, and I think I have it laid out in a slide in a moment, but we are assuming everybody's playing optimally right now, right? If an opponent is doing something incorrectly, if somebody's doing something incorrectly, their opponent will exploit that. Later, we'll talk about what happens if this assumption doesn't meet, if you're playing an inferior opponent. But for now, we assume everybody is playing the best possible strategy, or at least the opponents are playing the best possible strategy. In order to prevent the opponent from making an easy decision, the hitter is going to have to throw a fastball some of the time, the curveball some of the time, the pitcher is going to have to throw a fastball some of the time and a curveball some of the time. But the hitter is going to also have to plan for a fastball some of the time and plan for the curveball some of the time, because if he or she always plans for just one pitch, the hitters will be easily exploited as well. So each party will have a mixed strategy. Each action will be chosen with some probability and will be chosen less than 100% of the time in this particular game. So this a lot of the analytic work leads to finding out what exactly is this optimal percentage that the pitcher should pitch a fastball or the hitter should plan for the fastball. The answers to both of these questions I put up here, is there an optimal percentage? It is absolutely yes. What we spend a lot of time doing is finding out these percentages and in doing so, we solve for the mixed strategy Nash equilibrium. So for a mixed strategy Nash equilibrium, it would say the pitcher is going to throw a fastball X% of the time and a curveball Y% of the time, while the hitter will plan for a fastball A% of the time and the curveball B% of the time. So how do we solve for the mixed strategy Nash equilibrium? First, as we do with everything, we have to assume each side knows all of this information, and that each party knows the other party will behave optimally. Given these conditions, the best case for the pitcher is to make the batter indifferent between planning for a fastball or a curveball. So the pitcher's goal when determining how often to throw a fastball or throw a curveball is to make the hitter indifferent between those two choices. If the hitter is not indifferent between those two choices, it is not a mixed strategy Nash equilibrium, because the hitter is always going to want to do one thing or the other. But if the hitter always does one thing or the other, the pitcher shouldn't be mixing the probabilities. The pitcher should just exploit what the hitter's doing. The pitcher will be worse off if he or she gives the hitter an easy decision in this case. So the pitcher needs to mix the probability he or she throws a fastball or a curveball in order to make the batter indifferent. This is where we're going to leave off with part 1 of our mixed strategy Nash equilibrium lesson. If you go to the next video, we are going to go through the analytics of solving this. We're going to go through the algebra. So it's a jolly good time. So see you at the next video.